Where did we leave off? Life history and fecundity, survivorship curves and life history strategies. This is the fun stuff. Okay, so we left off talking about, I'm just going to go back a couple of slides. We started talking about demographics, life expectancy, age at first reproduction, things like that. We looked at survivorship curves, and we're really talking about, it's not just a matter of how long you survive or when mortality rates change, but it's also all tied in with your life history strategies and fecundity, which you guys may recall. Fecundity is a measure of basically, it's like lifetime fertility. It's how much you can reproduce under ideal circumstances. So no limiting resources, and you reproduce as much as you can, as many offspring as you can at every possible opportunity. So most organisms don't reach their maximum fecundity because resources are limited, right, always. But what we talked about was that inverse relationship between parental care and parental investment in one offspring versus multiple offspring, and how that affects those survivorship curves. Okay, so that's where we're sort of picking up. So we did not talk about these two terms because I felt like we talked about enough things last Wednesday, and rather than introducing these two new terms, because I don't think most people have heard these vocabulary words before. Talking about parity. So parity refers to birth, basically. So how many times do you reproduce is parity. So simulparity versus heteroparity, these are the terms that we're introducing here. A simulparous or organism, or an organism that displays simulparity, is only going to reproduce once in its life and then dies. So something like an annual. You guys know what an annual plant is, any gardeners? Yeah, what's an annual plant?
They just last for like one season.
Yeah, one season is done, right? So you have to replant them every year. They grow up, they flower, they set seed, and then that's it. But that's their life history strategy. That's simulparity. There are also animals that do this. So the examples that are listed up here are bamboo's on here as an annual plant, but you've also got Chinook salmon. They swim upstream, upriver to spawn, and then that's it. They just die because they only have to reproduce once. They make enough offspring that those offspring then migrate back to where the adults spend their life, and they keep the species going that way, right? So it's more about survival of the species than it is about survival of the individual in the long term for simulparous species. Saturday moths is another cool example. Have you guys ever seen a Luna moth? These guys are like huge, like, I don't know, 4 or 5 inches across, pretty big, pretty impressive looking. They grow from larvae like all moths and butterflies do, but the adults don't even have mouth parts, so they don't even eat. They just basically erupt out of their cocoon and reproduce and die. So they don't even have to like grow or repair anything, they just reproduce. That is the simulparity to max, okay? You're not even eating as an adult. Heteroparity, if you think about the term iteration, do you guys know what an iteration is, or iterative process? You've heard of that term before. If I tell you I'm going to reiterate, what am I doing? You guys know that word? Like, let me reiterate this for you. I'm going to tell you again, right? So iteration is basically like doing something more than once. So if you think about it in terms of iteration, heteroparity just means that you have multiple reproductive events across your lifespan. Okay, so it's sort of the opposite strategy as simulparity. And you may see reproduction only once a season, like something in, birds laying a single clutch of eggs or something along those lines every spring, but they live long enough to do that for multiple years or multiple seasons. Antelope is a good example, deer, eastern bluebirds, that's my little guy down here that I have. We have them on our deck. Sometimes they'll do 2 or 3 broods per season. Even. So they're definitely heteroparous. And then primates, right? We're heteroparous. We can have more than one offspring across our lifespan. Right? So that's just the difference between those two terms, but it's really important to also tie it in with thinking about life history strategies, right? And if you're going to, like, say, for example, you're simulparous, you're only going to reproduce once, something like a moth or a salmon or a bamboo plant, how many individual offspring do you think you're likely to produce at once? you're only going to do this one time, if you're simultaneous and you're going to reproduce and then die, are you going to just make one offspring, or are you more likely to make lots of offspring? Lots, yeah. Why do you think that? Yeah, you don't want to put all of your chances in one offspring if you know that's it for you, right? You're going to go more in the strategy of something like a type 3 survivorship curve, right? Where you make a whole lot of offspring because hopefully some of them survive, because you know you're not going to. So it ties back into those life history strategies, and it also ties into fecundity, right? The investment into individual offspring versus multiple offspring, and how much parental care you're going to devote to those offspring. So if you're simultaneous and you're going to die as soon as you reproduce, how much parental care are you planning to put into your offspring? None. You're going to die, right? That's it for you. Your life is done. Your lifespan is over. So it's all tying back in, right? Where if you see something that's heteropairous, you're probably going to have fewer offspring, higher quality offspring, and then spend more time taking care of them because you're around to do it, right? So it all ties together with these different things that we're talking about. And the last part of this that ties back in is population models and looking at K-selected species versus R-selected species. And when we're talking about K versus R selection, we're talking about two ends of a broad spectrum of life history strategies. Okay, so again, when we're talking about life history strategies, we're talking about how demographic factors like birth rate, age at first reproduction, number of offspring, death rates, juvenile mortality, infant mortality, all of those things add up to lead to adaptations that affect the way a population grows. So again, we're going to talk about dynamics. That's what we're talking about here, right? How populations change over time. And the next sort of subject that we're going to get into is talking about population growth. We're leading up to that by talking about reproduction, right? Because how does a population grow? How do you get more members of a population? Say again?
Produce more offspring.
Offspring, yeah, reproduction, right? So that's where we're sort of leading to. What about population decline? What has to happen for a population to decline in size? What'd you say?
Yeah.
Yeah, so when we're talking about populations declining, you're just talking about death, or you're talking about reduction in birth rate, right? So we're talking about birth rates, death rates, these life history strategies, but they're all also going to play into population growth, okay, which is where we're headed next. So these strategies, these K-selected versus R-selected, the type 2, type 3, type 1, survivorship curves, all of these things really play into how a population is adapted to where it lives and how it lives and what resources it needs, right? So just because you are on a type 1 survivorship curve like us, where we have one baby, take care of it for 18 years at least, and make sure that it survives and put all of our efforts into that one offspring, doesn't necessarily mean we're doing anything any better than something like a jelly, right? That's going to make thousands of offspring and hope for the best with zero parental care. It's just a difference in adaptation, right? It's an adaptation to a different set of circumstances that you find yourself in, right? It's where you fit. It's a product of your ecological niche. So when we look at K selection, these are species that are adapted to stable and predictable environments. Okay, you're not as much going to be threatened by things like starvation or predation. Right? Stable and predictable, you can devote more resources to each of your offspring and have longer periods of parental care. So something like a primate on a type 1 survivorship curve would be considered K-selected. And the K and the R don't really stand for anything. So I don't have any useful abbreviations for you there, except for sometimes the way I can remember it is that K is for kangaroo, and kangaroos have how many joeys at a time? Like one usually, right? They have to carry it in the pouch. So kangaroos would be K-selected. So maybe that'll help, just a silly little memory trick. But that would be one end of the spectrum, right? And then the other end of the spectrum is R-selected species, which are adapted to unstable and unpredictable environments. That would be something like our jelly example, or a dandelion with wind-dispersed seeds. It's sort of random species distribution pattern, and sort of takes its chances when it can. Large numbers of smaller offspring, so less investment into each individual, but making a whole lot of individual offspring at once. And individuals are largely self-sufficient at birth. They have to be. They can't require any parental care because these types of species aren't adapted to provide it. That makes sense? So it works, right? That strategy works because that's the type of strategy that they're best suited to do. It doesn't necessarily mean one is better than the other. It just means that it works for that particular species. But if you have to categorize an organism as K or R, it may not be as straightforward as an elephant. So what do you guys think an elephant? K selected or R selected? K, why? Yeah, 1, 2, maybe, right, at a time. And how long do you guys know how long elephant gestation is? How long do elephants stay pregnant with one offspring?
Too long.
Too long.
I think that isn't it like about a year or a little more than a year?
It's about a year and a half. Yeah, about 18 months. So that's a really long time, right? They got us beat by twice, right? And then elephant babies stay with their parents for a really long time too. So this is a really good example of K selection. What about jellies? What did we say they'd be, K or R? Yeah, totally, right? And then same with dandelions. But what about something like, a cat? How many kittens are usually born in the litter? 6 or 7, right? Upper limit probably about 8, maybe, right? Would you call that K or would you call that R? Or if you had a spectrum, and here's R and here's K, where's the cat? Yeah, so maybe like here towards K, but not completely, because it's like 8 babies, that's a lot of babies, and you do expect some mortality, right? Same thing with like a clutch of birds, right? If you lay 5 eggs in your nest, you may expect that 2 or 3 of those will make it, right? So you're still towards K because you're not making thousands like jellies, right? But you're making more than one. So there's definitely a continuum of strategy. So you're not necessarily going to be all the way to one end or the other of that sort of life history spectrum. Does that make sense? So it's really not necessarily that you have to categorize something into one category or the other, although you can, and you can make an argument as to why. But it's important to realize that, you know, everybody doesn't fit neatly into one category or the other, but they're sort of along a line, right, along the spectrum. So those are your population models. So you see how this all ties together. Survivorship curves, fecundity, investment, parity, and K selection versus R selection. Okay, so it's different topics, it's different terminology, but they're all related to each other. Okay, big picture as far as how organisms reproduce. Does that make sense? Okay, good with reproduction. All right, cool. Let's start talking about population growth. This gets pretty interesting, I think. So first thing we'll do is look at these 2 models of population growth. So what you can do, again, I told you, you probably remember that I said ecologists love graphic stuff. So we're going to look at some graphs here in just a second, but first we'll go through what each of these models means, and then we'll look at them on individual format. So these exponential versus logistic growth models, exponential describes a population that increases without limitations on its growth. So when you graph an exponential function, who has had those types of math classes where you graph functions? Probably most of you, yeah. You start, I think, in algebra, and then you move up to doing curves and stuff later on. But an exponential growth curve is going to show sort of a baseline of growth, and then it's going to, as it increases, increase leads to faster increase. Okay, we'll look at the graph here in just a second, like I said. But look at this, your population is growing or increasing without limitations. No limitations on space, habitat, no limitations on resources. How realistic do you think that is for most populations in nature? Peter, you're shaking your head. Why? Not realistic. Why? Yeah, absolutely. Competition, right? Resources are always limited. So this seems sort of unrealistic, right, in practice. So a good real world example that we can look at to start with here would be something like a bacterial colony or a bacterial population that you are growing in a lab under ideal conditions. Okay, so the example I have on here is in a large flask with plenty of nutrients that you are replenishing every day. right? So if you have a culture going and you're trying to keep these bacteria alive and reproducing, you can do that, but you are artificially creating that environment of unlimited resources, right? So in nature, nobody's doing that. Nobody's doing that for anyone, right? But if you have these ideal laboratory conditions, many species of bacteria can reproduce through binary fission in about an hour. So they don't have to undergo mitosis because they don't have a nucleus. So it's simple replication of that single plasmid and then split in two, just binary fission. It can happen really quickly. So if you have a species that reproduces like this under that sort of rate, then in an hour, 1,000 bacteria become 2,000, 2,000 become 4,000, and so on until after a day you have 16 million or more individual cells, right? And because bacteria are prokaryotes, a single cell is an organism, right? So that population of bacteria has gone from 1,000 cells to over 16 million cells in 24 hours. That is an exponential growth, an example of exponential growth. You guys understand? All right, so let's look at logistic. Logistic describes a population that has limits on its growth, and those limits intensify as the population increases. So instead of, like you see in exponential growth, where increase leads to more increase, with a logistic growth model, as the population grows, the pressure on that population increases, and competition increases, because there's the same number, this sort of limiting factor of resources that everyone is competing for. And so you start to see a slowing of the growth of that population as they reach what we call carrying capacity, okay? So we'll look at that on the graph too in just a second. So this is the more realistic model for pretty obvious reasons. Why is this more realistic? For most natural populations. What is it accounting for? Limitations, right? Limited resources, absolutely. So a population can grow as long as resources are plentiful, but as the population grows, resources become depleted and growth rate will slow down and level off. That's when you reach your carrying capacity. And what's a capacity? You guys know what that means? Say that a little louder for me. How much something can hold. When you guys talk, I can't tell who it is unless you I can just hear sound coming from that direction. Yeah, exactly. How much something can hold, right? Maximum capacity on the elevator, right? That's how much weight can get on there. How many people can be on there. Carrying capacity is the maximum number of individuals that can be supported by the limited resources of a habitat. Okay, let me show you on a graph. Here you go. Exponential versus logistic growth models. The exponential growth curve is described as a J-shaped curve. You guys see it? Looks like a J, kind of. So you've got population size here on the Y, and you've got time on the X. So you start with a low number of individuals, right? And then over time, you see the population grows because of the reproduction. And because there are no limits, and there's ultimately as much resource availability as anybody could possibly need, more individuals reproducing means that they are reproducing faster and your rate goes up exponentially. You guys recognize that as an exponential growth curve or a graph of an exponential function from math problems and stuff? It doesn't level off, it just keeps going, right? Until you're going straight up almost at a certain point. Logistic growth curve is described as an S-shaped curve. You can clearly see that S, right? And look here, the dotted red line is labeled for you. What is it labeled? Carrying capacity. So this is a pretend value. It's an arbitrary value, but this is where we're saying, okay, this is the maximum number of individuals that can be supported in this habitat. So maybe there's not enough space, or maybe there's not enough food. Things start to compete. So you see the same sort of pattern of growth in the beginning. So early in time, we have a low number of individuals, they start to reproduce, the population grows, and it starts to sort of take off, just like you would see in the exponential growth model. But then as the population increases, competition increases, right? Because you have more individuals competing for the same resources, so that the population can only grow, it's only able to grow slower and slower. as time goes on until you reach that maximum amount of individuals that can be supported, your carrying capacity, and then that growth curve is going to level off. Does that make sense? Can you kind of put the pieces together and see what's happening here as it grows and then competition kicks in and then that growth rate slows and then afterwards? Okay, good. Makes sense? Okay. So for these growth models, I'm going to ask you to be able to recognize examples. If I tell you a story, I'm going to ask you about the graphs. Is it J-shaped or S-shaped, and sort of what does that mean? Okay, so I need you to be comfortable with those logistic versus exponential growth models. But I also want you to understand that modeling is never going to fit. Your models are never, let me say this in a better way. Real world populations are never going to fit your models perfectly. Why? Why do you think? Yes, because the real world is crazy. The real world is the real world, right? It's dynamic, environments are always changing. Nothing is totally predictable in biology. You can model what you expect to happen and you can be close, but you can't expect it to fit the curve perfectly. And here are a couple of examples of that. So this first part of this figure, 45 comes from your textbook. The frame A is showing you a growth curve for yeast. Yeast grown in ideal conditions in a test tube show a classical S-shaped logistic growth curve. Well, it doesn't really look that much like an S. Right? It doesn't look as much like an S as this. So again, it's not perfect. Oops. But you can see your orange dots are your actual data points, right? So when you're looking at this graph, this is important to realize here. So these orange dots is time, amount of yeast, number of cells present at these different hour increments, and those are your data points, the orange dots. And then you can draw this blue line, and that's your line of best fit, right? The best fits your data. And you do see that it grows quickly until a certain point where resources become limiting, and then it slows, growth of the population slows, and then it levels off. So that fits the curve pretty well, okay? But this is yeast in a lab, okay? Even with that, you see that some of your data points are off the line, right? A little bit. It's a line of best fit, which means it's going to come as close as possible to going through all of your data points. Okay, but you can't get exact, otherwise it's not a line or curve. What I'm talking about. Okay, the second graph here, in part B of the figure, is a natural population of seals. Okay, from number of seals again on the Y and time on the X. So in 1975, you had low number of seals, and then you're tracing growth of the population over time. And then, you know, around 1990 or so, you start to see the population level out. You get a little bit of a dip here. So it's not a perfect S-shaped curve. Even the line isn't perfect, right? The blue line that you're looking at. But look at the data. What's going on here with these orange dots that's different than the orange dots in the yeast graph? Yeah, they're farther off from the line, right? They're not fitting that model exactly. So not only is the line a little bit different than what you might expect to see if you drew it perfectly like this, right? It's a little bit different, but your data is further away from that line of best fit. It's still a line of best fit. It's still a good curve, and you can still clearly see it's an S-shaped growth. It's a logistic growth model, but those data points are further away from that line. And all this is saying is that modeling is a valuable and critical tool in ecological studies, but interactions are complex. And it is rare for a real world population to fit a model exactly. That would be weird, in fact, right? Because the world is crazy, yes? All right. So what other types of things can regulate population growth besides resource availability and reproductive rates? And that's what we're going to look at next. We're going to talk about density dependent versus density independent factors that can influence the way a population grows. Okay, this is actually pretty straightforward stuff as well. So before we talk about density dependent versus independent, let's remind ourselves about carrying capacity. The carrying capacity varies based on things like season, climate, and natural events. So if the carrying capacity is the maximum number of individuals that a habitat can support, how might that change seasonally, then you think of a way that in one season, a habitat could support a higher number, and in another season, it could support a lower number of individuals. Certainly, drought conditions. What about winter versus spring and summer? Yeah, food is can be a scarcity in the winter months and things like that, where things bloom out in the summer and you have more bugs hatching and you have birds hatching and you have all this reproduction happening at this time of the year because it's warm and wet and temperate, right? And food is abundant. So carrying capacity is dynamic, just like any other value or any other measurement that you're using to look at population. So that's important to keep in mind. We're talking about other things that can affect population growth. Density dependent factors. All right, you guys, this is really tough. Depend on density. Right? It's tricky stuff. I'm kidding. The density of the population affects the growth rate and mortality. Okay, density dependent regulatory factors, that's the case. Things like predator-prey interactions are going to be density dependent. Now, what did we say density was? What is population density? Is it a count? Yeah, it is, right? It's a measure of population size, but then what else do you throw into the equation for density? Yeah, within a certain area, right? So density is like how many do you have packed into a particular space, okay? How many are there? If you have a dense population, you have more individuals that are coming into contact more frequently with one another, right? So if you think about predator-prey interactions, we talked about these before. Predators are those that go after and hunt and eat other organisms, and prey are the eaten. Yes, they're the prey items, the food items for the predator. So if you have a dense population of predators, how is that going to affect the population growth capacity of that predator species? You have a whole bunch of predators in the same place. Are they competing for, what are they competing for? Yeah, prey, the same food, yes. So that's a density dependent factor that regulates the growth of the population of the predators. What about prey? Do you think density can affect the population of the prey population? Or can density of prey items affect a predator population? Absolutely, right? If you have a whole lot of rabbits, that's really good for what? Lynx, things that eat rabbits, right? What if you have only a few? What if your prey population is sparse? What does that mean for your predator population? Yeah, harder to sustain, harder to survive because you have less food, right? So that's a density dependent interaction, density dependent factor for both predator and for prey. Interspecific and intraspecific competition. So inter is going to be between two different species, okay? Intra is within a particular species, but they're both really the same thing. It's competition. So when you think about density, let's talk about, let's just use our rabbit example again. So if we're looking at a population of rabbits and it's super dense, what does that do to competition for food? Dense population does what to competition, do you think? It's going to drive it up. Yep, it's going to increase. So that would be intra-specific competition for food, right? You can compete for mates, you can compete for habitat, right? But the more density, the more competition goes up. All right. So that would be density dependent. If you have too many organisms competing for the same resources, what is that going to do to population growth? You have a dense population and they start to hit that point where they're competing for resources. What happens to population growth? Starts to slow down, right? Until ultimately you get carrying capacity. All right, so that's how a density dependent factor influences population growth. Right, so I want you to know what they are, but I also want you to think about how they influence that population, because that's what we're talking about, is growth. What about parasites and disease? How is that a density dependent factor on regulation of population size? What do you guys think? Parasites and disease. Absolutely. The more dense the population, the more easily things like diseases that are communicable or parasites can spread. So if you have a disease that is ripping through your bunny population, your rabbit population that we've been talking about, and it's a dense population, that's going to have a more dramatic effect on the population growth of that dense rabbit population than it would on a sparse rabbit population. You with me? So if you have a population that starts out really dense and a disease rips through, you're going to lose more individuals than you are if you have a sparse population. When SARS-CoV-2 reared its ugly head last spring, what was the first thing they told us to do to prevent the spread? Before they even said everybody wears masks, what did they say to do? Stay away from each other, social distancing, right? That wasn't even a thing before. Now we all know what social distancing means. You need to spread out. It prevents the spread of disease, right? So that's how diseases and parasites are density dependent factors. If you have a dense population, it's going to have a greater effect on that population's growth than on a sparse population. So those should be pretty straightforward, yes? Make sense? So what about density independent factors? Well, these are going to be causes of mortality or limitations on population growth in a population regardless of density. They're density independent. So wait for it, it's independent of density, right? You guys with me? Okay. Natural disaster would be a good example. So we've got forest fire, a harsh winter, a drought summer, a tornado, a volcano, right? All of these things are going to affect populations regardless of how dense or how sparsely populated they are. Okay, so that's the difference between the two. But in reality, just like everything else, there's never like one or the other totally operating independently of each other. Okay, so both types of factors interact to affect populations. An example would be a dense population of deer affected by a harsh winter, which is density independent, right, will recover faster than a sparse population, just because there are more to start with. Right, so density independent and density dependent are always going to be sort of at an interplay with one another, but I just want you to understand that both are there, both exist. You guys good? Everybody on Zoom good? Okay, speak up if you need to. All right, let's talk about humans, shall we? Well, I gave away the spoiler. Human population growth is exponential. But you know what? That's kind of weird, right? Why is that weird? Why is the fact that our human population growth model looks like this? What's going on here? Why is this weird? What shape of a curve is that? That's a J-shaped curve, right? Classic. And this is data driven. So this is the population of the world from 1000 AD to present day. It's a little bit dated, so it sort of ends around 2000, but we're only 20 years out from this. It starts 1,000 years prior. And our population is way down here. This is population in thousands, so 1 million thousands. That's the first billion, right? A billion people. So at 1000 AD, we're well below that first billion, right? And then the growth of the human population is like, what's happening here from 1000 to about 1600, 1700, 1800? Pretty steady, right? So could I potentially take a red marker and draw a line right about here, a dotted line, and call that carrying capacity? I probably could, right? So something happens right around here that takes that carrying capacity and blows it out the ceiling. And the human population went, boom, exponential growth. First of all, before we talk about why is that weird? Homo sapiens is just another species, right? So we just said here that this is an unrealistic growth model. Unless you're in a lab and you're bacteria and someone's feeding you nutrient broth all the time, right? So what's going on here? That's weird, right? We should be subject to a logistic growth model just like other organisms. But we as human beings have come up with quite a few ways to increase our carrying capacity. Well beyond what it initially was sort of set at naturally. You guys, does that make sense? Okay, so this is just another graph of basically the same information, but putting it in a different set of terms. So this is the time between addition of billions of people. So remember we said here at the year 1000 AD, we were well below that first billion. It actually took until 1800 to hit a billion. We can see it on this graph, we can see it here. This line, do you guys know what this break right here means on this graph? This means that this line is way longer than what you can picture here. It's way bigger than scale. So this just indicates that there's distance on this bar that's missing. Because this is talking about all the time before the year 1800. How many years were Homo sapiens around before 1800? Which is, mind you, only, what, 200 years ago? How long has Homo sapiens been around in the fossil record? You guys remember?
200 million.
Almost 200,000. Yeah, we're babies, right? We're a blink of an eye in the evolutionary time scale. But still, 200,000 years, that's basically the length of that blue bar. Okay, so those, that break is all those hundreds of thousands of years. So it took 200,000 years to get to the first billion, right? But we said this population growth was really, really stable, probably leading up to this time as well. We're starting this graph at 1000 AD, but I would imagine probably pretty stable before that as well. So it took 200,000 years to get to the first billion, but it only took 130 years to get to 2 billion. That, my friends, is exponential growth, right? You go from here to this, start jumping. The next billion people were added in 30 years. The next billion in 15, the next billion in 12, the next billion in 12, and so on. That's quick, right? So now we're at about 7.5 billion on the planet. And that's right about in line with predictions. So this is saying we'll be at 8 billion by 2028, which is slowed a little from the 12 and 13 year gaps here. And then it'll only take another 26 years after that to get to 9 billion. The question becomes, what is this? What does this mean for carrying capacity in the future? How long is this sustainable? What do you guys think? Will we eventually hit another new carrying capacity? We don't really know. I mean, probably, eventually, right? The Earth is only so big. There's only so much habitable space. But even before you get to the point where everybody's shoulder to shoulder, like bacteria in a flask, right? Even before you get to that point, you have to think about things like food, right? Feeding 8 billion people. Already an issue, yes? Are there places where hunger is a problem? Are there places in this country where hunger is a problem? Yeah, right? So definitely something to think about. But how did we, before we start talking about the depressing stuff, how did we get here? How did we do this? How did Homo sapiens, as a species of animal, go about releasing ourselves from carrying capacity? How did we do that? What can we do? Why are we so freaking special? Well, there are some ideas, right? Well, intelligence is a big one. That's arguable in some groups, right? I kid mostly. Sociality and communication. So we are a very, very social species, right? And we tend to bond with groups, right? And within those groups, we can do things like communicate to solve problems. That cooperative nature is a big deal, along with the ability to communicate and intelligence, right? So we also know that with the evolution of bipedalism came this huge brain case, which evolution filled up with neurons, yes? So we have a huge brain to body mass ratio compared with other organisms. right? Like something like an ostrich that has a brain the size of a pea or a marble, maybe more like it, compared to you, where you have this big old brain inside your fairly big head compared to the rest of your body dimensions, right? So you're smart and you can problem solve and you can cooperate. So that's one of the reasons that we were able to do this, we think, hypothetically, right? So human development, how about building shelter? How does building shelter help you to release yourself from carrying capacity? Yeah, you're protected from the elements, right? You maybe won't freeze to death. You maybe will stay out of the rain and the lightning and things like that, right? So you make it a little safer. How about the development of agriculture, including domestication of animals? What do you think that did to humans, to Homo sapiens? Food supply increased, right? So if you are a hunter-gatherer, if you're a hunter-gatherer species historically, and then you figure out how to take the things that you're gathering and grow them in one place and cultivate them, what does that allow you to do as a species? Not just to have more food, but what does that food availability in that stationary place then allow for you to do? Community, yeah. So you start to see even more cooperation and sociality, communication, problem solving, and it sort of builds on itself from there. How about language? So the spoken word, right? We're not even talking about writing yet, but that's an important part of it too. If you can communicate with one another, and then you can start writing stuff down, you can teach new generations information faster than if every generation has to learn everything from scratch or instinct. Does that make sense? So if you have elders in a community based around growing some plants that you can all eat together, then the elders in the community can teach the youngers in the community how to keep growing that plant, right? They didn't have to figure it out from scratch. You can teach a person how to build a fire. You can teach a person how to hunt. You can teach a person how to build shelter, right? And you can pass that down at oral tradition first, right? And then you get written language, which means you can start to store information. You guys see where I'm going with this? How much better, how much more available is information to us in 2021 than it was in 1921? Just information. What do you think? My God, it's so much easier. I mean, even if you want to talk about 20 years ago, is anybody even 20 in here? Or are you all under 20? You're a little more than 20. You're looking at me like your eyebrows are off the road. How old are you?
I'm 30.
You will? I didn't know that. Well, let's say under 30. Okay? So that includes everybody. If I say under 30, well, I can remember 30 years ago because I'm 41. So when I was 11, we didn't have, the internet wasn't a thing. It was probably a thing. It was being developed, but I didn't know about it. Right? Like regular people didn't know about it. We definitely didn't have a computer in our house. We didn't have a cell phone. My kid was just asking me about this the other day. She said something about the olden days. Did they have some, when were flip phones? That's what she asked me. When were flip phones around? Like the olden days? And I was like, well, I guess that depends on what you mean by the olden days. If you mean like 15 years ago, then yeah, that was the olden days. But if you're talking about like when I was a kid, we used to like pick up the phone and you know, you were stuck to the wall because of the cord. She's like, doesn't even know what I'm talking about. She's never seen one. But if you think about information, so when I was in high school, my family got a computer. I was a senior, so I basically never used it. If you had a question, you had to go to the library and then use the microfiche. You guys didn't know what that is. Like the little films that you have to like put into a little projector and scan through to look for the Dewey Decimal Code, go find the book and pull it off the shelf and hope somebody else didn't check it out already, and then find the chapter and read it. And like 5 hours later, maybe you found an answer. What do we do now if you have a question? Yes, right? Oh, I just open my Google app and say, how do I get a dental crown? Right? That was a question that we were talking about earlier today. What actually did that? How did that work? You see what I'm saying? Information is like this. So that makes us better at solving problems even faster. So that's a really, really recent example in the history of the human population, right? But if you stretch that backwards, so we do go back to 1921. I don't know that much about history of things like telephones, but I'm not sure, did we have telephones in 1921 yet? I think it was late 1800s maybe when the phone became a thing. But you like picked up a thing and there was a lady there, she was like, what do you need? And you were like, connect me to Bob who cuts hair. You're like, hold on, right? Or could you mail a letter? Maybe, with a horse had to carry it, right? So the flow of information has changed tremendously just in 100 years. So if you think back to 1000 AD, communication is huge in survival, problem solving. Think about warning someone if something becomes, right? So that is a huge part of it. Our ability to migrate, right? Early man was curious and made it pretty far, all around the planet, right? But then now we can travel even more efficiently. We have colonized all the habitable land on Earth essentially. So we've taken over everywhere. So that releases us from space constraints in a lot of ways. This one's huge, you guys. Public health. So developments in sanitation and medicine, such as antibiotics and vaccines. Well, when did that happen? You know? When was the first antibiotic discovered? You guys know that one? That's a good trivia question. In Fleming's lab, it was an accident. That was in the 1930s, you guys. Less than 100 years we've had antibiotics. So what do antibiotics treat? Bacterial infections. What did you do before you had an antibiotic medication that you could take to treat bacterial infection? Say louder. Hopefully fight it off, or what's the alternative? Death. Yes? Lots of people died of bacterial infections, simple skin infections, right? Your innate immune barrier gets breached, bacteria get in, you go septic, and that's it for you, without penicillin and its derivatives and the ones we've come up with since then. That was only 100 years ago. So might that have had something to do with that carrying capacity? Disease, density-dependent population growth regulation, right? What about vaccines? Also widely available in the 19th and 20th century, right? When was the smallpox vaccine? Jenner, I think, was working in the 1700s, something like that. So not that long ago that we've had vaccinations. And things like polio and measles, all of those developments of those vaccines that used to kill people like crazy have been in the 1900s, mostly. Right, so in the last 100 years, 120 years, mostly that's when we've seen this huge increase in public health. So you don't die from something like strep throat. Okay, that makes a big difference in this growth curve right here, because you take that mortality rate and you drop it, right? Especially with juvenile mortality, things that would kill kids, things that we vaccinate against now. You're not losing so many people, so they're getting older and they're reproducing. Remember what happened in that bacterial flask? You start reproducing and more individuals are surviving to reproduce. That means you're increasing faster and faster because you've got more individuals reproducing. So that's hugely important. And then there's this, exploitation of energy in fossil fuels. What are fossil fuels? Give me some examples. You guys know what fossil fuels are, right? Coal and oil, things that you dig up, right? That's what fossil means. Really. Dig these things up out of the ground. What else happened around this point in terms of fossil fuel use and energy consumption and industry? What is the name for that big event or sequence of events that happened right around the late 1700s, early 1800s, continuing into the early 1900s? Industrial Revolution, absolutely. What do you think this is a coincidence? Like public health and the Industrial Revolution and this exponential growth curve of the human population? Definitely not a coincidence, right? Energy production, jobs, right? Which means money, which means resources, which means the growth of cities, all tied in with increased public health measures. Boom, carrying capacity gone, right? Yeah, it has a huge amount to do with it. So it was a slow progression towards about 1800, and then we shot through the roof. But here's where we get to the sad stuff. Sorry. These resources are finite. What does finite mean? Say again? They're not limitless. Infinite would be limitless, right? Finite is limited. At some point, we'll run out of fossil fuels. How long does it take for coal to form, do you think? We talked about those club moss forests, right? Way back in when we were talking about plant diversity, we talked about how they died quickly and got buried, and it was like millions of years ago, right? Those carbon-rich deposits of organic material under heat and pressure for millions of years turn into things like coal. But that took a really long time, a whole lot longer to form than it takes for us to dig it up and burn it, right? So we'll run out of that eventually. So what are we doing to address that problem? Things like, yeah, alternate fuel sources, right? Alternate energy, wind, water, solar, stuff like that, right? Hopefully that becomes more feasible as we move forward with the technology and public support. So long-term consequences, this is nothing that should be too terribly shocking for any of us, but a population explosion leads to the inability to feed the global population. So we have to think in terms of food production as well, right? We already see poverty and hunger in developing countries and developed countries if we're seriously taking a look at things, right? Inequalities in access to resources, which we already see on the daily basis, continue to widen as the number of humans increases. Because if you don't have access to resources like medicine or food or quality housing or sanitation, that inability to access those types of resources will only become exacerbated or get worse as more people are on the planet, right? Because of one key thing, competition, right? So we talk about things like increased disease, because what happens when you have a super dense population with disease? Easy to spread, right? Increased crime. Why? That one term, competition. Competition for resources, right? And of course, the ecological consequences, basically wreaking havoc on the natural resources of the planet. So these are the things that we are concerned about. And that's why you hear people talking about things like, fighting climate change and stuff like that, right? So continued change and degradation of the natural environment is another consequence of unchecked population growth. Alteration of ecosystems to the point of near collapse is already a reality. So we definitely have seen entire ecosystems wiped off the face of the planet, right? To make room for things like agricultural fields or expanding cities and things like that. Anthropogenic climate change, that's a term that you guys should know. I think we've used this term before, but anthropogenic means what? You guys know that one? What is anthro, like anthropology? People, yeah, man, right? So anthropogenic means produced by people, man produced, human produced. So climate change that is described as anthropogenic is our contribution by our activities to the climate change that's going on. So we're going to talk more about climate change in the later chapters. So this week, probably next week, we'll get to those chapters. But basically, it's cyclical. So you would expect to see warming and cooling in cycles naturally. Okay, so we're not responsible for 100% of it, but what we are responsible for is our contribution above the normal fluctuations. Okay, so we'll look at some graphs and we'll talk about what that looks like and what that means. But I'll go ahead and give you another spoiler. It's impactful. Okay, we definitely have some responsibility to be accountable for. Largely a result of burning fossil fuels, which releases carbon dioxide and other greenhouse gases into the atmosphere. And as I said, stay tuned because we're talking about this more later about the actual process and how the temperatures and the rainfall patterns and things like that are influenced by the presence of greenhouse gases and how that all works. So hold on to your hats because that's coming next. Many countries have implemented programs to decrease emissions of greenhouse gases, but it is an area of socio-political debate, right? Have you guys ever heard of anybody being a climate change denier? You heard that term before? What does that mean?
They don't believe that climate change is real.
Yes, that climate change isn't real, it's not really happening, or that this isn't part of it, that our activities are the problem, okay? So it is definitely a source of socio-political debate. Also, if you have to cut down on using fossil fuels, because fossil fuels produce greenhouse gases, who does not want you to do that? People whose money is invested in what? Fossil fuels, right? So you hear about the coal lobby and the gas industry and stuff like that, right? So we'll talk about that a little bit more later. Also, something to think about, in these developing countries, which tend to be more poverty-stricken than more developed countries anyway, let's say you are just starting to grow your economy through industry, and you are reliant on fossil fuels to do that and to continue that growth. And that continued growth means you can feed your people, and you can give jobs to your people, and your economy is starting to lift your population of people that live in your country out of poverty. How excited are you going to be about stopping to do that? You're not going to want to stop, right? But do you also probably not have the money to switch over from using fossil fuels to using solar or wind or water if you're not already set up with that infrastructure to do so, right? That's a big argument here, where we have the money to do it. But if you don't even have the money to do it, it's a difference between, okay, do I do the right thing for the environment, or do I continue to do the right thing that is lifting my people out of poverty? See where the issues come in, right? Talking about this kind of thing. Okay, so what can you as an individual do to address the growing human population that is putting stress on the planet and stress on our resources? What can you do? Here's a suggestion. You guys ever heard of the voluntary human extinction movement? Anybody seen this before? Jacob, you know what I'm talking about? I'm mostly joking, you guys. I'm not encouraging you to make yourself extinct, okay? So please don't take it that way. But this is a real group. So this is definitely fringe, right? This is definitely an extreme position to take, but it does exist. And I put a link to their website. I'm not sure this even still works, but you can click on it if you're interested or curious, because it's just interesting to know that there are people out there. They're saying their sort of creed is, may we live long and die out. So they're not encouraging that you go jump off a cliff. They're encouraging you to not reproduce, okay? Phasing out the human race by voluntarily ceasing to breed will allow Earth's biosphere to return to good health. Do they have a point? Sure. How realistic is it? Most of you are shaking your head. It's not realistic, right? People, listen, if it is hard enough to get a person to put on a mask because you gave them a mask mandate, how hard is it going to be to tell a person you can't have children? Can you even imagine, right? So this is not necessarily the solution, but it is an interesting sort of subset of people who belong to this group. Crowded conditions and resource shortages will improve as we become less dense. It sounds like they've had a lesson in density-dependent population regulation, right? Kind of an interesting tie-in, right? This is not a scientific group necessarily, but what they're saying is based in what we're talking about. Again, please don't take this as me advocating for live long and die out. I have 3 kids my own self, so I could definitely not subscribe to this group, right? But that's just kind of a joke. But it's also interesting to think about, right? All right, it's 12:01, so I'm going to stop here. It's also, we're switching to community ecology, which is sort of the second half of the chapter. So we can go through this on Wednesday. It's a perfect place to stop for today with the lectures.